Okay, so I guess I'm ready now, and give a little bit of rundown. So we have a couple things today to talk about. I actually had Lab Practical 2, and actually I think I'm kind of thinking if you're ready to take Lab Practical 2 and get it over with, maybe just do it. It's basically ready. I just want to tweak a couple things because people were misled by the way the wording was in the question. But the other thing today is there is an optional lab covering sensors and the Arduino microcontroller. So I only made like 6 copies of the lab. I can make more, but there's this is a lab that could be really interesting as a way to work with. If you're interested in computer engineering, microcontrollers are very essential devices. They're like little mini computers that interface really well with circuits so they can interface to the outside world. And in this lab, you get to this is the Arduino microcontroller, and you get to first start with some simple LED circuits controlling the LED blink rate, and then learning to write the programs that do that kind of operation. And then you can also, because the Analog Discovery also has an A to D converter inside it, you can sample a voltage in the range of 0 to 5 volts and turn it into a number from 0 to 1023. That's what the analog to digital converter does. It turns that into a number, which is really handy because then you can write software that uses that number, and you can basically use that to calculate what the position is of a potentiometer based on the voltage that it reads at the pin of the Arduino. So as you rotate the potentiometer, you can have it changing the blink rate of the LEDs. You can see how you can use that to control some other part of your circuit, which is a really nifty operation and pretty simple to do, kind of giving you the basic idea. Then you would you'll hook up a speaker, and you can send a tone to the speaker from the Arduino as well, and you can control the tone frequency with the potentiometer as well. So you can have a variable pitch tone coming out of it, and you can then at the end also look at that tone on the Analog Discovery, and you can see what the tone looks like as you're changing the pitch. You'll also see, I think, a bit of a step response because of that inductor. It'll sort of spike as as the square wave kind of turns on and off. And that's the culmination. You take a photo, you take a screen capture of the Analog Discovery. So it sort of ties together quite a few things in the lab, and I thought this would be an interesting lab to do. So that would be 100 points of lab extra credit if you do that. And then I was just sort of thinking about another lab which would be kind of fun to do, which is that application I was talking about yesterday of RLC circuits. And remember I mentioned that you can, what good are RLC circuits? They're a real pain in the butt. Well, there is a use of them in a boost circuit, a boost converter, which converts a DC voltage at one voltage value to a DC voltage at another higher value. And this is showing you it is essentially an RLC circuit. Here's the resistor, here's the inductor, and over here is the capacitor. But there is a diode and a transistor involved, which we've already worked with, and a square wave, which would come from the Analog Discovery. And what we're intentionally doing is we're flipping on and off an RLC circuit to generate a step response over and over again so that you get this spike. And it should be underdamped because you want it to overshoot pretty far and get a pretty high voltage spike that then sends charge into the capacitor through the diode. But then the charge can't come out because the diode's blocking it, right? The only way the charge can keep on going is through the load resistor right here. And I didn't try this yet, but I noticed this was on Circuit Lab. The nice thing about Circuit Lab is you can share schematics. This came from somebody else, but they were good enough to share it. And if we do a simulation, let me move this up here. We do a simulation of a time domain. Does anyone know what the time constant is of this RLC circuit? Alpha is minus R over 2L or something, right? Or is it L over 2R? R over 2L. So if R is 1 and L is 680 microhenries, you're going to take care of it, Matthew? Well, we kind of can tell it's actually triggering at 50 kilohertz. So we can use that as we want to look at maybe several cycles of that 50 kilohertz square wave. That should be good enough. So a 50 kilohertz frequency has a period of 1 over 50,000. 1 over 50,000 is 1/50th of a millisecond. That's 20 microseconds, right? That would be the period of one cycle. Now, if we want to see, like, say, 10 periods, we want to go maybe 0.2 milliseconds in our simulation. These are the kind of things you got to think about when you're running these things, right? So right now, this is going to 1 millisecond. That may be too many. Let's go to just 0.005. That'll be 50 microseconds, or yeah, should be a little more than, should be like, anyway. That's a stop time. And this time step, let's add another 0 there. And let's run this and see what it's doing. And what it's showing is the voltage. Wow, that's interesting. It was initially really quite high. It jumped up to 40, and then it tapered off. And at the end here, it was sort of dropping down to about 8 volts. I don't know why that would do that. That's very interesting. But maybe initially the swing and the inductor was so great, but then eventually it kind of gets into a rhythm. And then we're taking current out of it through the load resistor. So we're going from 5 volts to about 7.5, and you could see the capacitor is kind of averaging that. But if you change the components, like our inductor is 33 millihenries, and we have different capacitors you could try using, and you could try building this thing. I would actually maybe try simulating it first. You could start with the simulation. If somebody wants to try something like that and build it, I'll help you do that. You could get it all done today and just sort of experiment and see what kind of voltage you could get out of it, if that interests you at all. As another option. And then the other option is if anyone wants to take the practical, if anyone's ready. So I graded the lab practical 1 finally on like Sunday or Monday, and it was pretty sad. Quite a few people really are kind of confused about wiring circuits. Did you get my response? So if you're one of those people, that's another thing. I could give you some practice circuits that you want to just try building. Some simpler ones just to kind of get the hang of it if you're not sure. Because in Lab Practical 2, there's going to be some multiple choice questions where you have to identify a circuit. You're gonna get a circuit schematic from last year's students when they were working on Lab Practical 1, and it's a correctly wired circuit, but you have to look at the circuit and then figure out which of the schematics that are presented to you below matches the circuit that you're looking at. So it's kind of a matching thing. You don't actually have to draw out or wire up the circuit, but you have to identify which circuit you're looking at. Just a little bit of an easier problem, except some of the wiring is pretty crazy. They're using straight wires. They're not bending them, and some of them are all green, which I forbid this year. But that's not too hard. And then the other thing is you're going to do a Thevenin equivalent circuit. You're going to use Circuit Lab to determine the Thevenin equivalent of a circuit. and just using simulation. So you're going to find the open circuit voltage using Circuit Lab. You're going to find the short circuit current using Circuit Lab, and you know our Thevenin is the open circuit voltage divided by the short circuit current. So you divide those two, and you find the Thevenin resistance of the circuit as well. So that's sort of the operation that you get to do. So is anybody interested in doing the practical today, just to get it over with? This is a nice kind of an easy day. After this week, we're going to be doing. Well, after this week, we're going to be doing more structure. This is sort of an optional day, so you have a few things at your disposal. Next week, we're going to do starting in on AC circuits, and we're going to be pretty busy doing required labs from here on out. And yeah, so any takers, anybody interested in doing the practical today, just to get it over with? Maybe, okay. Yeah, I'm going to make a few touches, and then I'll release that. It'll still be due a week from Sunday, so you have time if you want to focus on first or second order circuits. Another thing you might want to do today is get any questions you have on second order circuits or first order circuits worked through, or you can work on anything that's kind of bugging you on that. Test is next week. And then the other thing is there is a final project option for the class. I even made a video overview of the final project. I can't remember what I had in there. So maybe we'll just take a look at it and see what's on there. If there's any demos, that would be nice, but it's just looking at the, yeah, I can do that. Well, this video is no longer available because the student that made it took it down. But this was Jonathan Hull's project from a couple of years ago. He made a personal alarm system. He wired up this circuit and designed it. He was really good doing his video reports. But he designed the circuit and laid out a breadboard, a PC board. Sent the design to China and got like 10 boards back for $50. So the op amp is generating a tone when that lead is removed, like an alarm if somebody runs off with your bag, yanks out the wire. Yeah, so he had a good time doing that, and he added this extra thing about making a PC board, which is kind of a cool outcome too. I haven't done that myself, but I'm sort of thinking at some point, it might be nice to add to the class. It could be another thing we do on the side. Making your own PC board is kind of a capstone sort of effort in working with circuits. But that's just one of many options you can do as a final project. Some of the others you can do are listed on this handout. And the handout talks about the points you would you would start with a proposal, and then a project report, and then I don't know if I mentioned this. This is an optional project, but you can apply the extra credit points to your circuits class, the Engineering 12 class. So most people are in more dire need for help in Engineering 12 than Engineering 12L. And that way, if you do this, you can get 3% of, if you do it all, well, you get up to 3% extra credit points for Engineering 12. And there's a few fun things you can do. There's a, this is an airbag trigger circuit, which is from the same source that Jonathan got the car alarm. I have a sensor that you could use for that. It's a piezo sensor. It is a it detects shock. It's a piezo crystal, and it's a really thin slice of a crystal. But basically, the crystal is of a material. I wonder if we look at that in the materials class at some point. It's called piezoelectric. When it gets shocked, it generates a pretty large voltage spike, and you can feed that into an op amp, which doesn't take any current at all, right? That voltage spike. Well, there's a load resistor there, so or an input resistor, so it'll go through there. But that sensor will detect a shock, and then when that shock is detected, the op amp will respond and try to track that at the minus terminal with a big, large spike here, and then that will kick off an airbag thing, which you'd have to kind of watch this on a scope. You could kind of see what this thing is going to do. It'd probably charge up the capacitor and hold it steady for a long period. So it probably takes like a really brief shock and activates the op amp, which then sends a high voltage at the capacitor. The capacitor holds it up for a while. Another thing, if you like audio, you can make a D to A converter out of op amps. I think it only takes. I have one quad op amp chip in your kit, so you just use one chip. You can make a 4-bit D to A converter. A D to A converter converts a digital signal into a voltage that you could then send. So it takes a digital signal which is made of 5 volts indicating digital 1 and 0 volts indicating digital 0, which we're going to look at a little bit in the Arduino. And you can connect that. So if you do the Arduino lab today, if this interests you, you could throw something together like this. You could make a crude music synthesizer. You could push button switches to trigger different musical notes, and a potentiometer to change frequencies, and LEDs to indicate which tone is playing. And there is an amplifier for the audio if you want to make a lot. Our audio circuit is a little bit weak with those. You can make a louder audio amplifier using another device, a 386. And that could be a way to get a louder signal. You could also run it into another speaker if you want. I mentioned before that you can use op amps to solve differential equations. We've been talking about that. This is a circuit that solves looks like a first order differential equation because there's only one capacitor in it, but you could solve a second order differential equation if you put another capacitor in it. And you could, you could write out the differential equation that it solves, and then you could run a signal into it of some source voltage, and then track the output as the solution for the driving signal. So this becomes the source voltage and this becomes the output of this thing, and that will essentially solve this differential equation for Vg of t. As I mentioned, this was a circuit that somebody did a few years ago, something like this, and got approval to have it apply for, is anyone in MATLAB right now on differential equations? Yeah, the one project, he looked at this differential equation with MATLAB, with Math32, and with a circuit, and wrote a report on what he discovered. This is a very cool lab, which I would love to work it into the class. This could be another fun thing. In fact, you could try to make some inroads on it today. But Kate told me it took a couple weeks for her students to go through this. This is a mock-up of a modern communication system. And what you would do is you would plug in your phone audio, like play some music, and you would play some music into an op-amp summer. Now, we did something like that, but in this case, the summer is designed to offset the signal so it goes between 0 and 5 volts, which is what the Arduino would like, or a typical A to D converter would like to represent the voltage waveform as a number. So the summer is actually increasing the gain and shifting with an offset of 2.5 volts. So it kind of goes between 0 volts and 5 volts and amplifies it so it's bigger. You get a nice cleaner signal. You then run it into an A to D converter. Now the Arduino has a built-in A to D converter. There isn't one else. There isn't an A to D chip in our kit, but you could use the Arduino to A to D convert the signal. And then you could spit those numbers out digitally at the Arduino, at different output pins on the Arduino. So the Arduino could act like a big A to D converter. So it's taking that audio signal, which you can hear, and turning it into a bunch of ones and zeros. Now at this point, it exists as a digital number. And the reason there's 1, 2, 3, 4, 5, 6, 7, 8 lines is because 8 bits of digital represents 1 byte of information, which could represent a number between 0 and 256. So you can send that information out, and at this point, because we have this analog discovery, which actually has a built-in logic analyzer in it, you could actually view the digital voltages on these lines at the same time. You can view 8 tracks of these digital lines. That's what a logic analyzer does. It shows you these things on top of each other, so you can watch the information flowing through the wires as digital information. And then you would build your own D to A converter with an op-amp, or four op-amps, I think. Or is it a summing? No, I think it's just one op-amp with, it's a summing op-amp, I think, that will allow you to build. Well, it has to be an 8-bit converter, so that would be a little challenging. You have to get 8 resistors that are powers of 2 of each other, that are multiples of 2 as they go. So like 100 ohm, 200 ohm, 400 ohm, 800 ohms, 1.6K, and so on, to be able to make a summing circuit that then would weight the different bits differently. Anyway, that constructs a single waveform, which you would then view on the scope. It would look something like this. You're basically reconstructing it again as analog, running it into a speaker, and maybe filtering out any additional noise that got inserted into the signal from the sampling. And then you can run it into your earbuds or to an external speaker. So that's basically what happens every time you talk to your friend on your cell phone. Your audio is being sampled and turned into a digital set of ones and zeros. And then it's transmitted from your phone as a bunch of ones and zeros to a receiver and the cell tower. And then they relay it to the other phone, and the other phone gets those digital ones and zeros and turns it back into an analog voltage, which you can then run through a speaker, and then you can put it, get it into your ear. The ear can't hear digital signals; it can only hear analog signals. So that's a really cool project. If anyone is interested in doing that, that is an option. Kate also provided some really interesting other op-amp projects. She has designed. She has a circuit where you design a voltage, a converting temperature, a voltage that represents temperature from a sensor, where maybe 1 degree Fahrenheit is 10 millivolts, into a Celsius. So you're doing some mathematical operations on a voltage to turn it from representing Fahrenheit to representing Celsius. Other people have done a musical pencil. This is a fun toy where the pencil itself, the graphite from the pencil, will conduct the electricity, and you can I think it goes through your body as well, like our lie detector test, and you can make a piano where you touch different parts of the drawing on your piece of paper, and it makes a sound. The pitch changes based on the resistance. It's not really a design project, but it's kind of fun. Solar chariots, those weren't actually too effective. I should probably pull those. A precision vision display is working with LEDs. Have you seen these? You can program the Arduino with an LED strip to represent an image, and basically it's flickering the LEDs like a raster scan, so that if you wave the circuit fast enough across your eyes, the LED leaves a trail like your eye is a raster printer. A bunch of dots, all the rods and cones in your eye record the position of the LED as it was sweeping by. You can kind of see the blur here that this person is making. It's like a pumpkin face. And you can actually display very ghostly images, like you can display words. People have put these on fans, and they program the fan. They program the LEDs to change with the frequency of the fan, so you can actually see words. You can put them on your car wheels. You can display messages to other drivers while you're driving, causing accidents. And then this is the boost converter that I was just showing you. We can, I think I actually rewired this, but I don't know. It says Lab 10 boost converter. I have to see if that's on my system still. This is actually what I just showed you at the beginning using components in our kit, a 33 millihenry, a 10 ohm, 5-volt square wave. Let's see if I can find this thing. And then there is the, if you want to plug something into a wall, this is how you would actually do it. You get a transformer, you run in 120 volts. Don't do this until you show me your design. And what comes out, the AC goes through a diode bridge, which turns it into a single-sided AC. So it's like a scallop, and then you run it into a capacitor to kind of average it out. This gives you a DC signal from an AC source. Any questions? Let's see if I can find this thing. It's called Lab 10. Yeah, there it is. So this would be a version that you could make with our Circuit Lab kit. And I thought it'd be kind of fun to do this. And it'd be nice if somebody actually built it. We could sort of document it, and then I could do a little write-up and maybe offer that as an option next year. So if we simulate this, let's see, simulate this with a, assuming that's set up okay. Oh, it's doing a lot of points. I don't know why it's set up like that. And here you can see the, yeah, we have a similar sort of kickoff transient. It starts off as high as about 80 volts. And then it tapers off here to about 15 volts. So we're getting about 15 volts from a 5-volt supply. So that's what a boost converter does. It takes a small voltage in and produces a higher voltage out. Now I turn this to a 10K resistor so that it wouldn't take as much current, so the voltage would be higher. You can design it based on your needs, but that's the basic premise, and it's got an RLC circuit built into it, which is kind of cool. So as I mentioned, so this is the final project. It's optional. You can get 3% extra credit for your circuit, for engineering 12 if you want, if you do this. 3% on your final grade of extra credit is not too shabby. But I know you're all pretty busy, so you have to sort of decide if that's something you want to do. All these options are here in the final project optional assignment. Any questions? Yeah, so anyway, if you want to do the Arduino project, that's the other optional thing you could do today for extra credit. I'll be around, and I will set up, I'm going to do a final tweak on the lab practicals, so if you want to take it today or before the weekend or whatever, you can do that. The rest of the class is yours.